Okay, starting slow, but remember, I warned you about that. This is not our most interesting section, but nevertheless, it's where we've got to start. Section 1, data. Data terms, ways of organizing data, data generally. When you're talking about data, you've got two concepts in play. One is the things you're interested in, and the other is what about them it is that is interesting. This is the concept of individuals and variables. So you could say that the individuals are the objects described by a set of data. All the people in the room, all the people in the city, all the trees in the forest, all the clouds in the sky, whatever it is you're talking about. And then the variable is what about the individuals that is interesting, a characteristic of an individual, if you like, something that describes an individual. So for example, if you're talking about, let's say, all the people in our class, then various variables you could use would be things like weight, height, age, IQ, hair color, eye color, major, social security number. Use your imagination. Well, let's be a bit more specific, shall we? Weight in pounds, height in inches, age in years, and not necessarily a whole number, of course. You could be 18.2 years old, etc. IQs, to the best of my knowledge, are, as it happens, in whole numbers. SAT scores, anything along those lines. So as you look at them, you'll notice that they tend to come in two types. On the one hand, we've got things like the red ones here, weight, height, age, IQ, where every individual has a number associated with it. Weight in pounds is a number, height in inches is a number, age is a number, IQ is a number, SAT score is a number, exam score, anything along those lines. On the other hand, you've got things like, in the blue, hair color, eye color, major. Let your imagination run loose. Where every individual falls into exactly one of several categories. These categories may be clearly defined, as in the case of major, a chemistry major, a psychology major, and so forth and so on. Or they could be somewhat arbitrary, how many eye colors are there? Well, for the sake of argument, blue, green, brown, other, 4 categories. Somebody else might make 10 or 12 categories. But every individual is lumped into exactly one of those categories. Likewise, how many hair colors are there? Well, whatever rules you pick, those are the rules you stick with while you're classifying people. So if somebody, let's take eye color. Blue, green, brown, other. So it's always helpful to have an other category, by the way, for things that don't fit the scheme. Someone could be bald, someone's major could be undecided, and so forth and so on. But every individual, let's take eye color. Every individual falls into exactly one of those categories. Let's think about that. So if someone comes along and they have blue eyes, then we'll put them in the blue-eyed category. If someone comes along and they have bluish-green eyes, we'll make a judgment call. For the sake of argument, I'm going to say that person has blue eyes, and we'll put them in the blue-eyed category. Or somebody else might choose to call it green and put them in the green-eyed category. Point is, the person with brilliant blue eyes and the person with bluish-green eyes, maybe a little more bluish, they're both in the blue-eyed category. And once they're there, once you're dumped in that category, your eyes are just as blue as anybody else's. In other words, there is no nuance preserved. There is only how many individuals get dumped into each category. And again, exactly one category, so you can't go into more than one category. That is to say, if you, for the sake of argument, let's say our categories are blue, green, brown, other. Every individual gets dumped into exactly one of those 4 categories. If we add up the number of people in the blue-eyed category, the number of people in the green-eyed category, the number of people in the brown-eyed category, the number of people in the other category, then it has to add up to how many we started with, not more, not less. For example, something like, what kind of movie do you like? would not be an example of a categorical variable, because you could like more than one kind of movie. You could dump an individual into the horror category and into the action category, and that's not the kind of thing we're talking about at the moment. For a categorical variable, every individual has to fall into exactly one of those categories. For a quantitative variable, every individual has a number associated with it. Weight in pounds, height in feet. Again, it could be a fractional number, 5.5 feet, and so on and so on and so on. Age in years, age in months, age in seconds, age in centuries, however you want to play that out. All they are is unit changes, and we'll talk about that a bit later. Then again, you've got something like Social Security number. What kind of variable is that? Well, let's think about it. What you want to understand is that everything we're talking about in Section 1 is very subjective. Things that are objective, things you can compute, we'll start talking about in Section 2. But everything in Section 1 is a judgment call. For instance, other books will use other names rather than individuals and variables. So if you see different terminology, particularly in the early part of the course, then don't worry about that. In the grand scheme of things, it doesn't matter what we call things, although it is nice if we're all on the same page for the purposes of this course. So I'm going to call them individuals and variables. Other books will call them by other names. But and likewise, you know, the number of hair colors, things like that, are also examples of things that are a little bit subjective. But whatever rules you make are the rules you stick with. Having decided that there are 10 hair colors, then you stick with that. And so forth and so on. But in a broader sense, you want to understand that these are systems that we have created because they are of use to us. They help us to organize our thoughts. You know, there is no cosmic objective sense in which something is one kind of variable or another kind of a variable. There's always room for gray area. There's always room for nuance. The bottom line is that we treat sets of numbers very differently than we treat where every individual falls into exactly one category. The bottom line is that they are two very different forms of analysis. So don't worry about whether some variable in some cosmic sense is one or the other. There's always going to be gray area. So take something like Social Security number or any other form of ID number. Well, it is technically a number, right? But it's not a quantity. It's not the kind of thing you have more or less of. You see, people can be lighter or heavier, they can be shorter or taller, they can be younger or older, they can have higher IQs or lower IQs. We're talking about quantity, right? Number line, movement on a scale, less, more. Social Security number is not that kind of thing, right? There would be no point, for instance, in averaging two people's Social Security numbers together. If you've got the largest Social Security number of anybody in our class, then congratulations on you. Nobody cares. It doesn't signify anything. It's not a size. It's not a quantity. For all the difference it makes, there may as well be letters in there, right? We are in no sense treating it like a number, a quantity. On the other hand, it's not really a categorical variable either, right? It's true we could make some categories. We could have Social Security numbers that end in 0, end in 1, end in 2, 3, 4, 5, 6, 7, 8, 9. We could have 10 categories in that way. Or any other way you want to organize it. You know, Social Security numbers from 0 to whatever, from whatever to the next one, and so on and so on. There's all kinds of ways you could organize those things, but you could do the same thing back here, right? You could have people under 18, people from 18 to 30, people from 30 to 40, and so on. You could always make categories, but it misses the point. In a different situation, yes, maybe you want to talk about children, young adults, older adults, seniors, and treat them as categories. But that's not what we're doing at the moment when we assign a number to everybody's age, to every person. So the bottom line comes down to what form of analysis are you going to do? There's always room for thinking about things in different ways, sure. I mean, for that matter, you could attach numbers to the various majors, but in no sense would that become a quantity. Chemistry major is not so much more than a psychology major. It's a totally arbitrary decision, right? So the bottom line is you would never treat Social Security numbers as the kind of thing you have more or less of. On the other hand, any categories that we could make would probably be artificial and not have any real world meaning either, right? So when the ultimate real world question is, again, what kind of analysis are we going to do? Are we going to treat them like quantities, numbers on a scale, or are we going to treat them like categories into which the individuals have been lumped? We would never really do either with Social Security number, right? There would really never be any reason for analyzing people's Social Security numbers. I mean, never say never, right? I mean, there's always interesting things you can do if you've got government funding and money is no object and you're bored out of your skull. You could look at how the different numbers in the Social Security numbers correspond to different geographic regions. Are there more people with higher Social Security numbers in California than there are in Florida? Sure, why not? If you're bored, there's always some kind of analysis you could do. But the bottom line is, as we look at this, we're not going to be averaging these things together. And on the other hand, there are no natural categories either. So the important thing to understand is there's always going to be things that don't fit our scheme. You don't want to be too pedantic about anything we're doing in Section 1 because it is subjective. But the bottom line is that we do a very different type of analysis with a set of numbers than we do where every individual falls into exactly one category. Units, the way we measure a quantitative variable, we'll talk about units incessantly throughout the course, but the bottom line is that you could talk about somebody's height in feet, or their height in inches, or their height in centimeters, and those would be different sets of numbers as far as that goes, right? It would still be everybody's heights. Conceptually, it's the same type of data, but numerically, they would be different numbers if we did them in feet or inches or centimeters, right? The distribution of a variable, what values it takes and how often. In a word, the pattern. What kind of pattern does the variable have? Now, the thing to notice is that this is very vague and subjective, and we'll talk about it more as we go. You don't talk about the distribution of a variable as an abstract thing. You talk about the properties of the distribution, whether it's like this, whether it's like that, whether it's like the other. And the first thing you want to notice is that categorical variables have a very different kind of distribution than quantities do. And that's what we're going to talk about for the most of the rest of this section. Gender, sex, let's say sex, keep it simple, male, female, or female, male. Again, there's no logical order to those categories. There's no logical order to eye color categories. There's no logical order to majors. You could do them alphabetically. You could do them in some other way. But one person's order for these categories is just as valid as somebody else's order to those categories. Very different thing from over here, right, where there is a natural order, low to high, for weight, age, IQ, height, etc., right? So not only are there very different kinds of distributions, but categories and quantities have very different types of distributions. So there's not going to be one word that sums this all up, but pattern is basically, I think, closer than anything else. What kind of pattern do we have to these situations that we create? Now, as far as categories go, we can dispense with them pretty quickly. There isn't a lot to say about categorical variables. The bottom line is if we're talking about a bunch of people, then all you've really got is how many individuals have been lumped into each of these categories. So for the sake of argument, we're talking here about 85 people, and we've got 4 eye color categories for the sake of argument. So 25 of the people in the room or whatever have blue eyes, 12 have green eyes, 42 have brown eyes, 6 have other. And, this is, it's not going to let me, this bit here is what we start with, right? We start with 25 people with blue eyes, 12 with green, 42 with brown, and 6 with other. And the bottom line is, that's all you've got, really. There's a number of ways of snazzing it up, as we'll see in a second, but there really isn't that much more to be said. And again, for instance, remember when you're assigning people to these categories, it might be an easy call, someone with very blue eyes, or it might be a tricky call, somebody with bluish green eyes, or bluish brown eyes, or bluish gray eyes. But regardless, 25 people have been dumped in the blue-eyed category, and as we look at the screen here, that's all we know. We don't know how blue they were, or how many were an easy call, or how many were a hard call. All we know is that there were 25 people that were dumped in the blue-eyed category, and so on and so on and so on. Now again, note that there is no logical order to these categories. Blue, green, brown, other, green, blue, other, brown. Any order you care to list them off in. Now it is true in this particular example, not so much for something like major. You're either a chemistry major or a psychology major. You're not sort of halfway in between or closer to a psychology major. There's no nuance there whatsoever. But for hair color and eye color, there's plenty of room for nuance. Again, you could have bluish green eyes. But on the other hand, you could have bluish brown eyes or bluish gray eyes, call it other, or greenish brown or whatever. So while it is true that there may have been some nuance in the beginning, number one, it is no longer relevant. When you're talking about categories, it comes down to how many individuals have been dumped into each category, and looking at the screen, that's all we know. 25 people, however blue their eyes were, have been dumped into the blue-eyed category, and that's all we know. There is no nuance left as we look at what we have here, if there ever was any. So, and on the other hand, for point number two, even granting that there is nuance, it is in no sense one-dimensional nuance, right? You could be 5.99 feet tall, or you could be 6 feet tall, and they're pretty close to the same thing. But that's not what we have going on here. While it may be true in the past that you could have bluish green or bluish brown, it isn't movement on a scale, It isn't one-dimensional. It isn't like blue is the smallest and other is the biggest. So even if there ever was any nuance, number one, it is not relevant any longer, and number two, it isn't necessarily one-dimensional nuance. There could be all kinds of ways that these things could create nuance with one another. You could have one eye blue and one eye brown, for instance, in which case maybe we'll put you in the other category. Now, the fact that there is no nuance remaining, if there ever was, justifies what we call the gaps when we go to display this. The way to display categorical data is with either a bar graph or a pie chart. We'll talk about that in a minute. But before I get to that, let's talk about what else is going on in this frequency table. Now, frequency is just a fancy word for how many. So, some kind of label here, right? It doesn't really matter per se. Frequency, number of people, thousands of turnips, whatever you're talking about, but something to tell people what you're talking about. Frequency is kind of jargony. Number of people, we'll say it very nicely, and so forth and so on and so on. What can we do? Well, we can add them up, right? So if it wasn't already given to you in the first place, you could certainly add them up, and logically you better get 85. Let's see, 11, 12, 13, 14, 15. Yeah, so it looks like it adds up, right? So it's always nice when things add up, right? But for the sake of argument, let's say that this total was not originally here. Well, first thing we could do with this frequency table is we could compute it. Now again, there aren't that many things you can do with categorical variables. All you've really ultimately got is how many have been dumped into each category. Yeah, you could compute a total. The only other thing you could really do numerically is you could, the only other way you could complicate this, the only way you could add any further knowledge, as it were, to the bottom line being right here, is you could divide it out, right? So you could find some percents. So 25 divided by 85, let me just grab my calculator very quickly. 25 divided by 85 is 0.294117 something. So for no reason whatsoever, I'll round it and call it 0.294. 3 places. Well, percents, of course, are out of 100, so multiply by 100, 29.4117 something. Now I'll call it 1 place after the decimal, 29.4. So divide by the total, and for percents, multiply by 100. I just want to scan it. Okay, there we go. So I'm going to talk about that a bit later. So 25 divided by 85 times 100, 29.4%. It's all in the name, right? Percent out of 100. Likewise, 12 divided by 85 times 100 is 14.1, and so forth and so on. Now, just for giggles, let's add those up. 29.4 plus 14.1 plus 49.4 plus 7.1 is exactly 100%. But it didn't have to be, right? There could have been rounding error. Remember, 0 to 4 you round down, 5 to 9 you round up. Let's look at this again. 25 divided by 85, 12 divided by 85, 42 divided by 85, and I don't know if I can get these all on the screen here at the same time on my calculator, but 6 divided by 85. Yeah, just about. So what am I looking at here? 0.2941 something, rounded down. 0.1411 something, rounded down. 0.494 something, rounded down. 0.0705 rounded up. So some of them are going to round down and some of them are going to round up. You've got no control over that, right? And particularly if you've got a lot of categories, we really don't. Well, probably about half of them will round down and half of them will round up, right? But what if they don't? It's luck of the draw, really. So if more of them round down than round up, then theoretically this could add up to 99.9%, right? Or if more of them round up than round down, then theoretically it could add up to 100.1%. Or, however you choose to round it. I'm doing 1 place after the decimal here. So 99.9 wouldn't really surprise me. 100.1 wouldn't really surprise me. Rounding error. They should add up to 100%. If it's a hair off, that's rounding error. If they're adding up to 70, you made a mistake. So things to be aware of. Now, of course, wherever there's rounding, there's the possibility of rounding error, and that'll be with us for the whole course. But there's a flip side to that. Wherever there is no rounding, there is no possibility of rounding error, right? So if it's 25 actual people, 12 actual people, 42 actual people, 6 actual people, then it better add up to 85. Or the 85 is wrong. On the other hand, there could have been rounding, right? This could represent a large city, right? Thousands of people. Well, not a very large city, maybe a large town. But what if this were thousands of people? Literally, THOUSANDS of people. Then I'll call it 25, THOUSAND people, and so forth and so on and so on. Now, probably it wasn't 25,000, right? So if this has been pre-rounded, 25,000 people, let me try that again, 25,000 people, right? That's our units, 1,000 people. 25,000 people, 12,000 people, and so on and so on. Then, of course, there's been rounding, and it may not add up perfectly, right? If the total has not been provided, well, add them up, provide it. If the total has been provided, then wherever there's rounding, there's the possibility of rounding error. But if it's actually 25 people, etc., then there's no rounding in this column. There's no possibility of rounding error. Things to look out for. So basically, that's all we can do with the data we have at hand is once we've created our categories, we can add them up or we can convert them to percents or some other things that we'll talk about later, proportion and so on. So when it comes time to display them, once you've got your frequency table, in particular we'll just stick with this original bit here and never mind the totals and the percents, then we can create a bar graph. A bar graph is a way of displaying categories. Let me try that again. Wherever you have categories, you have a bar graph. Wherever you have a bar graph, you have categories. So there are things that look like bar graphs that are not bar graphs, and we'll talk about those a bit later. And of course, journalists and whatnot will get it wrong, but strictly speaking, wherever you have bar graphs, you're talking about categories. So bar graphs, as opposed to some other things we'll talk about a bit later, histograms, have very specific properties. Well, you get the basic concept. Before we get into that, blue, brown, green, other. For some reason, I have put these in a different order than I have in the frequency table, but that just kind of makes my point. So blue, brown, green, other, there's our categories. Why that order? Why not? Why not some other order? Go for it. So there's no logical order to the categories. There's gaps between the bars. They don't necessarily have to be as wide as the bars, but you do want to aim for some consistency. All of the bars should be the same width, and all of the gaps should be the same width as one another. If the gaps are a little narrower than the bars, it looks a little nicer. Than this. If the gaps are a little bit wider than the bars, it starts to look a little weird. So the gaps in the bars can be different from one another, but all the bars should be the same and all the gaps should be the same. What does this... Oh, okay, well, before we get into that, you get the basic concept, right? So this is height 25, frequency, number of people, whatever it is we're talking about, number of people. That's 25, obviously, right? And the green is 12 over here, and the brown is 42 here, and this is meant to be 6, so that's about right. So we've got our bar graph. You get the idea. The height of the bar represents the frequency. Now, there's no reason you couldn't do it as a percent, with this representing 29.4%, and so on and so on. If you're creative enough and careful enough, you could relabel this existing bar graph so that this is height 29.4, and this is height 49.4, and this is height 14.4, and so on. I wouldn't advise trying. It won't end well, but theoretically we could do it, right? We could relabel this scale, whether we're talking number of people or percent of people or any other way of looking at that. It's just a unit change. It's just a relabeling of this bar. But we'll stick with raw counts, frequency. Other observations, it begins at 0. Some books will tell you that it's vitally important to start at height 0 or this is going to be deceptive. Other books will tell you that it's not that important, but what I would tell you is that that is among the more obvious of the choices that you can make here that are going to affect the display you're seeing. For instance, if you start this thing at height 5, then this last bar over here is going to be very, very short, and so on and so on. Or if you want to get sarcastic, why not? Start it at height -10, and then we can make all the bars look longer. That would be silly. But the point is there's any number of display choices you can make here that are going to affect your visual patterns. Relabeling this axis is only the most obvious of them. How physically fat or thin you make these bars is another one. You see, there's a thing. People don't look at this and see height. That's not the way the human mind works. People look at this and see area. So for instance, if you make the green bar 3 times as wide as the other bars, then you're going to make it look a lot bigger. You're going to make it look a lot more important, even if it's the same height, right? So it's a very bad idea to make these bars different widths. That's going to be deceptive. Now, mine is not to judge you. On the one hand, you'll learn the proper ways of doing things so that you won't deceive people when you go to use statistics. On the other hand, you learn all of the creative ways that you can deceive people when you go to use statistics. It works in either direction. If I want to be cynical about it, I would say there's a greater living in the latter. But mine is not to judge you, mine is just to teach you proper practices. Be aware that if you start tampering with the widths of these bars relative to one another, then that's one way you're going to deceive people. If you make the brown bar thinner than the other bars, you make it look less important. If you make the other bar wider than the other bars, you make it look more important. Human beings aren't looking at this and seeing height, they're seeing area. So that's why you want to have a standard width for all the bars. Otherwise, you're deceiving people. Alternately, that's how you deceive people. So what can we say about a bar graph is, number one, there are gaps between the bars. The categories are separate entities. If there ever was any nuance, there may not have been. Major didn't have any nuance. But yeah, eye color, there's probably room for judgment call on who ended up in what category. There may have been nuance in the first place. But it wasn't one-dimensional nuance, and it's not relevant any longer, not once we're working off of this. We're going to get the same bar graph, whether these 25 people had the bluest eyes you've ever seen, or whether they all had bluish-green eyes, slightly more bluish. Right? The nuance is not relevant. So there's no nuance or flowing into one another, whether or not there ever was in the underlying concept before you began. So to preserve in spirit the idea that they don't flow from one into the other, that they're separated categories, we always have gaps when we do a bar graph. There's no horizontal scale. Why? What does this width for blue represent? It represents absolutely nothing, right? It represents an aesthetic choice. Make the bars too fat and it looks weird. Make the bars too thin and it looks weird. You want to make it look nice, but beyond that, the width of this bar has no mathematical significance whatsoever. There's no horizontal scale here going on, so this distance represents absolutely nothing. There's nothing numerical going on horizontally. And on a related note, there's no logical order to the categories, right? It isn't like blue is the smallest and other is the biggest. Somebody might say, let's do other green, blue, brown on the logic that it looks nice if the bars are ascending. Somebody else might say, let's do brown, blue, green, other on the logic that it looks nice if the bars are descending. Somebody else might say, let's do it alphabetically, which is in point of fact what I've done, but I'm sure it's a coincidence. What's the bottom line? Looks nice, looks nice, looks nice. Arbitrary subjective choices on our part. There is no logical reason to do it in this order rather than any other order. So there's no logical order to the categories. It's basically the same bar graph if we list the categories off in some other order. Of course, the brown one should still be the tallest and the other should still be the shortest, whatever order they're in. So that's really it for categories. The only other thing you could do with categories is a pie chart. Well, before we get into that, let's talk about for the course, for the long haul, this is a very important idea. The following all mean essentially the same thing. Relative frequency, how much out of 1? Proportion, how much out of 1? Percent, how much out of 100? They're all just different ways of saying the same thing. Well, relative frequency and proportion are almost exactly the same thing. The relative frequency out of 1. The relative frequency of people with blue eyes, 25 actually divided by 85, rounded of course, is 0.294. The proportion of people with blue eyes is also 0.294. Now, if you're talking connotatively, there's maybe a very thin hair difference between the two. Relative frequency kind of implies a decimal, whereas proportion kind of implies a fraction, 294 divided by 1,000. But numerically, it's exactly the same thing. The proportion, the relative frequency of people with blue eyes is 0.294. The relative frequency of people with brown eyes is 0.494. The relative frequency of people with other is 0.071, and so on and so on. Start with relative frequency, just divide by the total. Proportion, divide by the total. To turn it into percent, we'll multiply by 100. So mathematically, we'll multiply either one of these by 100 to turn it into percent. But apart from that, they are basically all the same thing. They're just three ways of saying the same thing. Relative frequency, proportion, percent. One that you may not have thought about is probability. Now we'll do a whole section on probability, and in a broader sense, the whole course is about probability. But for now, well, let's put it this way. People overthink probability. So we'll talk about this a lot as we go. But for our purposes, the probability of something happening is just the proportion of times it would happen. So for instance, if you mix these people up and pick one, then you've got a 0.29, it's out of 1, like the first two. So numerically, it's exactly the same as relative frequency and proportion, 0.294 for blue eyes. So if you mix these people up and pick one, then there's a 0.294 probability they'll have blue eyes. If you mix these people up and pick one, there's a 0.494, almost a half, probability that they'll have brown eyes, and so forth and so on and so on. So the thing to understand is that probability is not more complicated than that. People overthink probability. Yeah, there's a lot of things to say, and we'll say them. All of section 4 will be about probability, but we've got a lot to do first. But people overthink probability. For the moment, let's just say that it's just another perspective on the same thing. Wherever you have data, you have probability. Mix them up, pick one. What's the probability you get this, that, or the other? So wherever you have data, you have probability. On the other hand, wherever you have probability, you have data. If you have a fair coin with a half probability of coming down heads, well, flip it 100 times. Head, tail, 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 head, 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 tail, 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 head, tail. Now you've got data. So if you've got an abstract probability situation, do it a few times, generate some data. Roll the die 1,000 times. Now you've got some data. On the other hand, if you've got data, mix them up and pick one. Now you've got probability. So it literally is just two perspectives on the same thing. Probability, data. Now there's a lot to say about that, and we'll talk a lot about that in the middle part of the course. But it's a good starting point. It's a good way of thinking about things. Wherever you've got probability, you've got data. Wherever you've got data, you've got probability. Sometimes it's easier to think about things one way than the other. You could say that half the time you flip a coin it'll land heads, or you could say there's a 1/2 chance it'll land heads the next time. In the end, it's the same thing. Now, fingers crossed, there's a lot of nuance in that statement, and we'll talk about it as we go, but that's the basics. And if you want a fifth one, we'll throw on percent chance, right? Same idea. If you pick somebody, then there's a 29.4% chance they've got blue eyes. It's still a probability-ish perspective, chance I mean, but now we're talking about out of 100 rather than out of 1. So in the end, they're all just different ways of saying the same thing. Now bear in mind, you always want to tell people what you're talking about, right? So you better make it very clear. There's a big difference between a 29.4% chance and a 0.294% chance, right? So you want to be very careful what you're talking about. 29 out of 100, 3 out of 10. That's what we're talking about when we're talking about blue eyes. 0.294 out of 100 would be a lot smaller. It would be less than 1%. It would be about 1/5 of a percent. Take that back up. I'm thinking 0.2, but you get the idea. So you do want to be very careful. Make sure that you're clear on what you're doing. Make sure it's clear whether it's a percent out of 100 or a proportion out of 1. Label things so that it's clear what you're doing. But as long as you're consistent about it, it doesn't greatly matter which of those perspectives you use. As for pie charts, we're not going to get into them too much. This is not a course in constructive geometry. You don't need to have a compass and a straight edge to take this course. So I'm not going to ask you to draw pie charts. It would be tedious and it would accomplish nothing. But you should at least recognize a pie chart when you see one, because they're not that complicated to look at. They're tedious to produce, but they're not that complicated to look at. So a pie chart here, I don't know why I picked red over here. I guess it was just the default on whatever program I used it for. But you get the idea, right? First of all, notice that the pie chart has to use relative amounts. Out of 85 is not going to give you anything like a pie chart. Out of the whole thing, out of 100, out of 1, that will give you a pie chart. So it doesn't matter whether you do percent or proportion necessarily. I've put it as percent here. But bear in mind that the wedges represent how much out of the total, how much out of 100, how much out of 1. So this is 29.4-ish of the total arc distance, a little more than a quarter, a little more than 25%, right? The green one, on the other hand, is 14% of the total distance, right? The brown, 49.4%, so the brown is almost half of the total distance as we circle around this thing, right? And the other is 7%, so, well, put it this way, it's the smallest of the wedges, whereas the brown is the biggest of the wedges, right? Now, everything we said about bar graphs is still more or less true, not the gaps necessarily. This program has a nice white line separating them, but that's not really that important. But the stuff about the order is germane, right? Blue, brown, green, other. Well, first of all, you could rotate this thing to your heart's content so that the brown is on the top here, or the bottom, or over here on the right, and it's going to be the same pie chart, right? On the other hand, you could do them as we go clockwise here. You could do them in some other order, right? Blue, other, green, brown, or some other order. So where things are situated relative to one another are not important, and what order they're in as we go around is not important. But of course, the relative sizes are important. We can see at a glance that about a quarter of the people have blue eyes, a little more, and about half the people have brown eyes, a hair less, which you wouldn't necessarily get out of the original counts. So to do the pie chart, you have to use the relative amounts. So let's see, we're coming up on 45 minutes, so I think we'll leave off here for this particular video. And that basically tells you everything you need to know about how to organize categorical data and how to display categorical data. Again, I'm not going to ask you to draw a pie chart. And in fact, as we go on, my interest in categorical data is this is not the most important thing going on in this section. The most important thing in this section will be quantities. That's a typo, by the way, and I'll talk about that in the next video. So we've just finished categories, and this will be quantities coming up. That's a typo. So categories goes to here, and coming up on 45 minutes, I think that's enough. So the important part of this section is yet to do. We'll do part 2, displaying quantitative data, in the next video.